How's exam 3?
Like exam 2. Similar to exam 2.
Similar? Did we fare well? We don't know. Well, I'll have the scores up this afternoon. As for the previous exams, each Q will be worth 14. Now, let's get at finishing chapter 23. An aspect of Bronsted-Lowry acidity which we did not talk about last time. I had a note about it on the board, but didn't take time to mention it. No big deal. Solvation. Note that this word is not salvation. I have not the wherewithal to provide you with salvation. If I could, I would, but I can't. This statement is, I think, obviously a reference to how solute and particles derived from solute interact with solvent molecules. No more, no less. This will be a very important consideration in organic chemistry, because in organic chemistry, the Bronsted acidity of a number of different acids will be considered in a number of different solvents. Not so important for us because we're limiting our considerations to water chemistry. But to illustrate, Ka acetic acid in water. Many of you probably have this number memorized, 1.8 times 10 to minus 5. If we were to observe Ka for acetic acid in methanol, as solvent, and this investigation has been done, would we get a Ka value in methanol for acetic acid, which is 1.8 times 10 to minus 5? Or would Ka acetic acid in methanol be bigger than 1.8 times 10 to minus 5 or smaller than 1.8 times 10 to minus 5? What do you think? The answer to the question lies in realizing what you get when acetic acid does its acid thing. In water, we get hydronium ion and acetate ion, AQ. However, in methanol solvent, what do we get? We again get acetate ion. But now you can't make hydronium ions. You don't have any water molecules to protonate. Instead, you protonate the methanol molecule, which we considered early on in chapter 18. If I protonate this molecule, where goes the H+? Here. No place else to go. So we've looked at the reaction products. But now let's take a step further. In water, solvent, water molecules interact with hydronium ions and acetate ions. Do they interact favorably with hydronium ions and acetate ions, these water molecules? What do you say about that, Coulomb? If you're a hydronium ion, would you interact favorably with a water molecule? Coulomb. If you're an acetate ion, would you interact favorably with a water molecule? Coulomb. Yes or no? Yes or no? Yes. Of course. Why? These are both electric particles, aren't they? Hydronium ion and acetate ion are obviously electric particles. They're ions. They bear absolute charges. Water molecules is highly polar. Water molecules are highly polar. So the negative end of the water dipole, the oxygen atom end, by Coulombic attraction, will stick naturally to hydronium ion. In the positive ends of the water dipole, the hydrogen atom ends stick naturally to the acetate ion. Does this produce a stabilizing effect on the presence of ions? You remember when we talked about the possibility of making H plus and HO minus in the vapor phase? H plus gas and HO minus gas. We compared that to the possibility of getting water molecules to react with each other to produce hydronium ion and hydroxide ion in water solution. Now the extent of that transformation is quite small, as reflected by the tiny value for Kw. But if I heat water molecules to the point of their decomposition in the vapor phase, will I get hydrogen atoms and hydroxyl groups, neutral HO particles? Or will I get H plus and HO minus in the vapor phase? We did this. You don't make these positive ions in the vapor phase. You got no solvent molecules to stabilize their presence. Nothing to insulate them from each other. Positive ion, negative ion vapor phase, they're going to attract each other quite potently. There's nothing to interfere with this attraction. No insulator. No solvent. But this can happen in the liquid phase. So with that being said, in which of these liquids can this ion creation process take place more readily? Water or methanol? Which of these liquids will do the better job of supporting the presence of charged particles in their presence? Water. Why? It's more electric, isn't it? It's more polar. You betcha. Ka for acetic acid in methanol is a good deal smaller than 1.8 times 10 to minus 5. Enough said. That's what solvation is about. If solvent molecules interact effectively, favorably, with particles that are produced by dissolving a particular solute in water, like acetic acid, which reacts with the water to make charged particles, hydronium ion and acetate ion, hey, that will stabilize these ions. Whereas methanol will not stabilize the presence of ions nearly as effectively because it's not nearly as polar. In any case, enough on that. One question which we did not consider, although at this point we are able to consider because we've already discussed the considerations which underlie such. This is at the end of the discussion in Chapter 23, the discussion of stabilizing effects on Bronsted-Lowry acids, which are molecular in character. So far, all our conversation has been devoted to such. HCl HBr, perchloric acid, perbromic acid. Periodic trend-wise, we found out which of these acids is the stronger. Which is it? This one. Stronger. Between these two, however, which acid is stronger? Well, let's put that one on hold for a moment. HCl does its acid thing, we get chloride ion. Br minus does its acid thing, we get bromide ion. Which of these species stabilizes negative charge density more effectively? Well, it has to be bromide ion because HBr is the stronger of these two acids. So this conjugate base is a weaker base than this conjugate base, which means this negative charge is stabilized somewhat more effectively than this negative charge. What simple device did we use to rationalize this? We couldn't use electronegativity, because the electronegativity of this is 3.0 for this 2.8. That would support the conclusion that HCl is the stronger acid, would support the conclusion that Cl minus is the weaker and more stable base. But that doesn't fit the facts. But we go back and recognize En 3.0, En 2.8, these En values are rather close, aren't they? But the size difference between these two is substantial. They're derived from halogen atoms in different periods. So we picked on charge to size ratio, didn't we? And that fit the facts. Because if I smear a minus charge over a large surface versus smearing, again, 1 unit of minus charge over a much smaller surface, hey, here the negative charge is far more concentrated based on charge to size ratio. So you can write depends on size, or if you wish, charge to size ratio. We've done that. Now back to these two. Let's take these species and turn them into the anions for these species. Perchlorate ion, perbromate ion. Now remember the size differential we observed between these two anions. Chloride ion, bromide ion. Now we're going to take these two and convert them into perchlorate ion versus perbromate ion. I got to move you over. If I now compare sizes, clearly perbromate ion is larger than perchlorate ion because this atom is bigger than this atom. But do I have a size difference which is near as great as the size difference I had previously? If I take one ping pong ball and one marble, not a marble like this, do I see an appreciable size difference in favor of the ping pong ball? All right. Now, let me add to the ping pong ball and its volume, or surface area really, 100 marbles. Let me add to the marble with which I began 100 marbles. Clearly the volume of the ping pong ball plus the 100 marbles exceeds the volume of the 101 marbles. But do I have a size difference which is anywhere near what I had when I had the one ping pong ball compared to the one marble? Heck no. You can make an analogy of this to money. How about a quarter versus a nickel? The quarter's bigger and worth 5 times as much. All right? Now let's dilute each by combining them with pennies. A quarter plus 5 pennies, I got 30 cents. A nickel plus 5 pennies, I got 10 cents. The quarter versus the nickel is 5 times as valuable. But when I diluted each with 5 pennies, then the value ratio has fallen off to 3 to 1, hasn't it? Same idea here. You don't have near the size difference between these two as you had for the chloride ion all by itself versus the bromide ion all by itself. I make this argument because we have to pay attention to the fact that this is the stronger of these two acids, whereas here this is the stronger of the two acids. So I know the difference in acid strengths between these two, with this being the stronger acid, can't be a consequence of this, because that would support the conclusion that this is the weaker base, and it is not. For these two, this is the weaker base. For bromide ion, chloride ion, bromide ion is the weaker base. So what other arguments that we have previously considered, stuff you had on your mind for last evening's written exercise? At least I hope you had this stuff on your mind. What sort of arguments did you have on your mind that would relate to this? Well, induction, 4 peripheral oxygen atoms. But this is a little bit more electronegative than this. Anything else? Bond angles. None of these are structurally identical. They're both tetrahedral. Maybe it'll be somewhat easier for you if I look at each of these anions from a Lewis structure standpoint. This Lewis structure for perchlorate ion, and such would be the same for perbromate ion if I just erase this and write in Br, shows the maximum degree of multiple bonding which minimizes the overall degree of formal charge. If I have 2 single bonds and 2 double bonds, then I'll have 2 -1 oxygens and a central atom plus 1. 3 single bonds, central chlorine atom would be plus 2 and 3 -1 oxygens. If I go to all single bonds, plus 3, and each peripheral oxygen would be -1. Always giving rise to a net charge of -1, but this Lewis structure shows the least degree of formal charge. So on that basis, formal charge reduction, I'll opt for this Lewis structure. But this Lewis structure is somewhat misleading, don't you think? Because this Lewis structure suggests resonance is a very important property for this ion. Now, resonance is a property for this ion, but is resonance as important for this ion as it is for this ion? Stuff we've talked about. No, because this is trigonal planar. All the component atoms are sp2 hybrids. Here, you can argue sp2 hybrid for the peripheral oxygen atom, but you can't argue sp2 hybrid for the central chlorine atom. It's sp3. It's tetrahedral. If chlorine, or bromine if I turn this into bromate ion, perbromate ion, if chlorine is going to be able to participate in multiple bond formation with oxygen atoms, can the chlorine atom use valence p orbitals to do this? If chlorine is going to participate in multiple bond formation with the peripheral oxygen atom, and that's what these Lewis pictures suggest, because I got pi bonding. Okay. Can the chlorine participate in this pi bonding and resonance with valence p orbitals? Yes or no? Yes or no? How many valence p orbitals does chlorine atom have? How many? 3. And they're all tied up in the sp3 hybrid. They're all part of the sigma framework. So if chlorine for perchlorate ion and bromine for perbromate ion in fact participate in a degree of pi bonding with the peripheral oxygen atom, can't be using p orbitals. So how is this possible? D orbitals, how about those dirty dog D's? Remember I showed you a model of d orbital. You can take a look at a picture of these in chapter 24. Probably you saw models of d orbitals in 2040, but I don't know for sure. So, from a theoretical standpoint, because for this Lewis picture, chlorine is +1, and these oxygens are each -1, the singly bonded oxygens. If I play this game, I'm using p electron density from this peripheral oxygen to add to this bond site and become part of a pi bond. So what this really is like, this pi bond formation that we're talking about here, is a Lewis acid, Lewis base reaction. Right? Remember Lewis acid, Lewis base? Lewis base does what? Supplies the electron density to make the bond. And what's a Lewis acid supply? Empty valence orbital to make the bond. Now this obligates you to remember what the heck Lewis acid, Lewis bases are about. Well, what empty valence orbitals does chlorine atom possess in its valence environment, which can be used to make pi bonds and accept this p electron density to make pi bond? 3D. You betcha. Okay? Lewis acid, chlorine with empty 3D orbs, valence orbs. Now, if we erase this, put in bromine atom, then we got the same species, the same structure for the other species, the perbromate ion. Okay? Why can we argue that this structure is expectedly somewhat more stable than the corresponding perbromate ion? Why can we argue that pi bonding for perbromate ion ought to be somewhat more effective than for perchlorate ion? Pi bonding for perchlorate ion. Why can we argue that pi bonding for perchlorate ion ought to be somewhat more effective than pi bonding for perbromate ion? What did we consider that relates to this? Remember that? What's that? Well, exam 3's over, so we forgot that already. That's gone. Principle of maximum overlap. Most effective orbital overlap. Regarding orbital size is achieved when the orbitals which overlap from each other are similar in size. Well, that means they got to come from atoms which are similar in size. And chlorine and oxygen are more close in size than are bromine and oxygen. So what we wind up with is a case that can be resolved by PMO considerations. And why do we apply this rather fanciful argument? Because it fits the facts, that's why. Because perbromate ion, perchlorate ion, chloride ion, bromide ion, all these, they don't give a damn what we say and what we think and what we write and what we theorize and what we calculate. They never did and they never will. If you have anybody teaching you science who gives the impression that Mother Nature behaves in accord with theories that we cook up, phooey, you're dealing with a charlatan. Mother Nature doesn't give a rat's hoo-ha about theories that we cook up or what we think. Never did and never will. We cannot impact behavior of nature by our thinking and by our writing and by our calculating. Now, we sure as hell can impact how Mother Nature behaves by shooting off hydrogen bombs, but not by thinking. So when we cook up, when we observe nature and its behavior, it's our job to come up with arguments which fit the facts. Because the facts are them. That's what's real. There's only one bottom line dictator in science class. I'm sure I said this to you before. That's the experimentally verifiable fact. That's it. Not thoughts, not ideas, not theories, not textbooks, not Horvath, and not anything else. That's it. So we apply this rather fanciful argument because it fits the facts, no more, no less. And now, let's talk in brief about hydrated metal ion acids. I mentioned these in passing during our conversation on Wednesday so as to remind you we wouldn't ask you about hydrated metal ion acids on exam 3. I decided to do that on purpose because I found out from past experience that you folks, and I'm very sympathetic, you're just learning this stuff. So if I jam the hydrated metal ion acid stuff in with all this other stuff we've been talking about, you start going after these hydrated metal ions with ideas like PMO and electronegativity and Lewis structures and all that stuff, as well you are expected. But that doesn't apply to this case. For example, if we wish to talk about the difference in acid strengths between these two, structurally they're identical. Shape-wise they're identical. The only difference between these two is the hydrated metal ion itself, aluminum ion versus magnesium ion. What do we know about the difference in acid strength between these two? Pardon me. You folks in the lab know this for sure. Which of these is the stronger acid by far? Aluminum ion. So, how can we rationalize this? Well, if the only difference between these two is aluminum ion versus magnesium ion, then the answer has to lie in the differences between aluminum ion and magnesium ion when they are hydrated, to make these hydrated metal ions which have this shape, octahedral. This hydrated metal ion has what shape? What do you bet? Tetrahedral. But here's another hydrated metal ion that's octahedral. Most common shape for hydrated metal ions is octahedral. Likely you remember that from the stuff we did in chapter 22 on electrochemistry, given that all the hydrated metal ions, with the exception of silver ion, that we considered in chapter 22 and are part and parcel of certain of the half reactions, were these hexahydrates, octahedral species. There's a water molecule. Don't these nice red loops look like non-bonding pairs? That's what they are. Okay. So, here's our model. One of these, any one of these white spheres that's part of our model is this thing. Okay? Lewis-based water molecule approaches Lewis acid aluminum ion and makes a connection. In so doing, a non-bonding pair converts to a bonding pair. The aluminum ion supplies another model fell apart. These models are one of the few things around here that's older than I am. I can fix it, but it'll take some time. Okay. So, non-bonding pair on water molecule converts to a bonding pair and becomes the chemical glue which holds the water molecule as a hydrated species onto the surface of the aluminum ion. So why should hydrated aluminum ion, why should a water molecule that's connected to an aluminum ion why should this water molecule stick more strongly to aluminum ion than this water molecule sticks to magnesium ion? Positive charge density. It's going to attract negative charge density, the non-bonding pair, more strongly. Now, in what way does that relate to the fact that this water molecule has a more acidic character than this water molecule? Because when these hydrated metal ions behave as Bronsted acids, they do so by forcing cleavage of an OH bond of one of the hydrated water molecules to break heterolytically. Right? This breaks, and off goes H plus into solution, likely connecting to a water molecule to make hydronium ion, versus this breaking. Goes off into solution as H plus, Connects to a water molecule, make hydronium ion. Why is this OH bond much more readily fractured heterolytically than this OH bond? Well, this bond is shorter and stronger, isn't it? Because this has a greater positive charge density. That means that this distance, hydrogen atoms of a hydrated water molecule to the aluminum ion itself versus hydrogen atoms of a hydrated water molecule to the magnesium ion itself, which of these distances is shorter? This one, isn't it? Because this bond is shorter and stronger, and this is a smaller ion, isn't it? Aluminum ion is smaller than magnesium ion, isn't it? They're both isoelectronic with neon, but this thing's got 13 protons pulling on that config versus 12. So this is smaller. That brings this H plus closer to a greater positive charge concentration than over here. That makes this HO bond more readily fractured. Now we're talking about Coulombic attraction in conjunction with Coulombic repulsion. Sites of positive charge lead to repulsion, leads to H, leaving is H plus. That's it. So all you really need to do to compare the relative strengths of hydrated metal ions as Bronsted acids is to pay attention to the positive charge density of the metal ion. That's it. Provided the metal ion is noble gas structure. Ne, noble gas structure. Ne, noble gas structure. What's this guy? Helium, noble gas structure. This acid, stronger than this acid. How do these two compare? The hydrated metal ions are both +2. But which of these metal ions is a good deal smaller? I'm pointing at it, am I not? This is helium. This is Ne. So this acid's stronger than this acid. How do you think these compare? Now notice you have competing factors. Here you have greater charge, but a larger ion. Here you have less charge, but a smaller ion. So if I tell you that if I give you size data and you calculate the positive charge density of beryllium ion to be about the same as the positive charge density of aluminum ion, what would you say about the relative acid strengths of these two? About the same. There. How about that? Interesting. Now, how about this character? What do we know about Ka for this character compared to Ka for this? If you don't remember, look at the acid-base table. This is a hell of a lot stronger acid than that. Tell me. As isolated ions, how does the positive charge density of Fe plus 3 compare to that of Al plus 3? As isolated positive ions. Which one is assuredly smaller? Aluminum ion. Hey, that's neon configuration. I mean, iron plus 3 starts with an argon core. And to top that off, it still has an abundance of valence electrons. Specifically, how many? Iron plus 3. How many valence electrons does it have? And what are these valence electrons? Iron plus 3. Well, let's start with the iron atom. 26 electrons. If I want to make iron plus 3, I've got to take away 3 of these electrons. What electrons are remaining that are part of the valence structure? Well, let's start with the whole configuration. Argon, which accounts for 18 electrons right off the bat. How many 3d electrons? How many 4s electrons? 5 and 2? Argon is 18. What do I have to add to 18 to get 26? Huh? 18 plus what number gives me 26? All right, we got through that part. And these 8 electrons are valence electrons for the iron atom, which has the configuration 3d6 4s2. So when I take away 3 electrons to turn iron atom into iron plus 3, which of these electrons did I take away? 4s pair and one of the 3ds. So here's iron plus 3 with 5 valence electrons still remaining. All 3ds. A hell of a lot bigger than aluminum plus 3. How can that damn thing be a lot stronger acid than hydrate aluminum plus 3? It's fun, isn't it? Now then, do you remember a few days ago watching this video, which I think number-wise at that time was 00036, which had the date July 12. And in this video, there was this Oscar award-winning star, movie star. Remember who that was? And in that video, we talked about things like penetration and shielding and Z-effective and all that kind of stuff. Well, let's let the facts talk to us. Because if this damn thing is a much stronger acid than this, which it is, because Ka this is 4 times 10 to minus 3 versus Ka this, which is on the order of 1 times 10 to minus 5. This thing's almost 400 times stronger as a Bronsted acid. But this ion is bigger than this ion, which means as isolated ions, this ion has a smaller positive charge density. How the hell can this be the stronger acid? It must be true that water molecule iron plus 3 bond interactions are stronger than bond interactions here. That has to be the only way this thing can be a stronger acid. So, we dig into our theoretical bag of tricks and go back and pay attention to this shielding and penetration and all that kind of stuff. Because as soon as the oxygen atom uses a non-bonding pair to bond with the iron plus 3, then those valence electrons are no longer a part just of the oxygen atom. Now they're a part of the whole thing. What do we know about these electrons that the oxygen atom has used to make this coordinate covalent bond? If I asked you to identify non-bonding electron pair for the oxygen atom, what are you going to tell me about their nature? Energy level 2, energy level 3, are they S electrons, P electrons? What are they?
Energy level 2, P.
Well, the oxygen atom in the water molecule is hybridized how? How's it hybridized? sp3. But this sp3 hybrid is derived from orbitals what energy level? 2. Hey, do you think energy level 2 S and P electrons can penetrate effectively through 3D electrons? I mean, from an electron stacking standpoint, would energy level number 2 electrons be inside 3D electrons and closer to the nucleus? Well, yes. So let's play this game. Let's imagine that these electrons, which the oxygen atom uses to make the coordinate covalent bond with iron plus 3, because they're derived from energy level number 2, have a rather substantial penetrating ability. And when they penetrate toward the iron plus 3 nucleus, What kind of positive charge are they looking at? What's the Z value? 26. Is that good deal bigger than the Z value for aluminum? So now we got a way to explain it. It's fanciful, but I don't give a damn because it fits the facts. We're going to argue because the 3d valence electrons shield poorly. These energy level number 2 electron types from oxygen can penetrate through these 3d electrons, make a stronger bond interaction with iron plus 3 compared to the water molecules interacting with aluminum, and for aluminum plus 3. Makes a stronger water molecule to metal ion bond, leading to more ready heterolytic cleavage of an OH bond, accounting for why hydrated iron plus 3 is a stronger acid than aluminum plus 3. Hey! How about this? There's hydrated gallium ion. What relationship does gallium share with that of aluminum? The same family, aren't they? Is gallium plus 3, is that a noble gas structure ion? Is gallium plus 3 a noble gas structure ion? Yes or no? It is not. Why is gallium plus 3 not a noble gas structure ion? Gallium plus 3 has a 3d10 collection of electrons. That's not noble gas structure. So if the story I just cooked up to argue why hydrated iron plus 3 is a much stronger acid than hydrated aluminum plus 3, and we know that gallium plus 3 is a lot bigger than aluminum plus 3, but this is not a noble gas structure ion. It's got a full complement of 3d electrons, and these 3d electrons are showing themselves to be lousy shielders, which means I can get a stronger bond interaction of water molecules, non-bonding electron density, which becomes bonding electron density when these things hydrate, with gallium plus 3 than I can get here. So if I put all this stuff together, how will I expect Ka for this to compare to Ka for this? Expect Ka for this to be bigger. So in order to find out if this fancy story bears any weight, what information are you really going to look for? No, you're not. You're going to go to Wikipedia or someplace and look up Ka for this thing. You're going to find out if this is stronger than this. And guess what you're going to find out? You're damn right it is. It's considerably stronger than this. How about that? So I'll stick with the story because it fits the facts. So we'll stop there and pick it up with the rest of this stuff next time.